Hello, 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 Physics 11 students. Hello, hello, hello. All right, we're taking a look at the 7.6 review, questions 1 to 6. This is impulse and momentum. Momentum. Not that you could read my writing, because that's just the day it is. I hope you guys are doing well. For no good reason, but I hope you're doing well. All right, so just to remind you, or let's just do this quick review. Momentum is a vector force that is found by taking the mass, multiplying it by the velocity. Impulse is a force that is a vector quantity that is happening for a certain length of time. Impulse, that's impulse. And impulse is also a change in momentum. That's also impulse. So we'll engage our impulse engines and see what we can come up with. An object is pushed with a force of 6 newtons per 0.5 seconds. What is the impulse? All right, so we take a look at this. We find force is equal to 6.0 newtons. And then we have this 0.50 seconds. Well, this is the time. This is our force. So we're asking for an impulse. So F delta T will give us our impulse. We don't have, there's not like a symbol for this. You know, it's not like this is capital I or even IMP, like we're just talking impulse. So we'll take our 6.0 newtons, we'll multiply that by our 0.50 seconds, and so that's going to be equal to 3.0 newton seconds. There is our impulse. Question number 2. What impulse produces a velocity change of 4 meters per second in a 12.5 kilogram mass? All right, so this is the idea that our change in momentum is equal to impulse. And that's equal then to our change in mass times velocity. Is the mass changing? No, just the velocity is changing. So we can say that this is mass times our change in velocity. Now, we're not given this in terms of an initial mass or initial velocity and final velocity. So this is really what we're going to be using. So if we take our 0.4 meters per second, well, that is our change in velocity, just to continue with this format. And then we have this number of 12.5 kilograms. Well, that's then our mass. So we can substitute in these values. So our impulse will be equal to our mass 12.5 kilograms times our velocity, change in velocity of 4 meters per second. So if we go 12.5 times 4, we get a value of 50 newton seconds, and that's our impulse. So that's just the way we keep track of things and use things. All right, so let's go on. Here we have a 15 kilogram wagon is accelerated by a constant force of 60 newtons from 0.5 meters per second to 13 meters per second. What is the impulse? All right, so we have 15 kilograms. That's our mass. We have a force of 6.0, sorry, not 6.0, but 60 newtons. And then we have a 5 meters per second, and that would be an initial velocity. And then we have a 13 meters per second, and that would be a final velocity. So if we're asking for an impulse, well, we can take a look at that as a force times our change in time, or we can take a look at that as a change in our momentum. Well, we have no time, so we're not going to use this. We're going to use this in order to calculate our momentum. Either of these is an acceptable way of doing it, and which one we use depends on the information that we're given. So if we take a look at our delta mv, Our mass isn't changing, it remains. So what is going to be changing is our change in velocity. And so that's going to be our mass times our v minus our v naught, our final velocity minus our initial velocity. So our mass is 15 kilograms, our impulse that we're trying to find. Our final velocity is 13.0 minus our 5.0. So this is 15 kilograms. And 13 minus 5, well, that's equal to 8 meters per second. And so if we go over 15 times 8, that's equal to 120 newton seconds. There's our impulse. Then the question is, how long was the force acting upon it? So we're looking for our time. Well, impulse is equal to our change in our momentum. That's also equal to our force delta t. So we know that these things are equal to 120 newton seconds. So even though we calculated from here, we can use this to calculate the next part. So we can go F delta T is equal to my 120 newton seconds. And the force we were told was 60 newtons. So we'll use 60 newtons delta T is equal to 120 newton seconds. So delta T is equal to 120 divided by 60, and that would be equal to 2 seconds. That's how long the force was acting upon it. I'm really trying to emphasize this idea that impulse is equal to this or this, and that we can use either of those to calculate. There's something that students seem to miss, it's that sort of idea. Here we have a freight car with a mass of 6 times 10 to the 4th kilograms is rolling along a level track at 0.4 meters per second, dragging a chain, a force. If the chain provides a force, so we've got, here's our wheels, there's our freight car, and it's on our train track, and for some reason there's a chain that's behind it. We should put some graffiti on there. Trains always seem to have graffiti. Oh, all right, how long is it going to take to stop? So this impulse is equal to our change in momentum, and that's equal to our force times our time. So we have, what information do we have? We have 6 times 10 to the 4 kilograms. That's a mass. We have a 0.40 meters per second. That's a velocity. And what we have is a force that's equal to 320 newtons. And then they're saying, how long does it take to stop? Well, that tells me this, we have a final velocity that's equal to 0 meters per second. So how are we going to use this information? Because really, how long does it take to stop? That's our delta t that we're looking for. And so we're going to have to use this whole thing together in order to calculate this. So if we break this up, we have mass is equal to our v minus our v naught, our final change in velocity, and that's equal to our force times our time. So our mass, 6 times 10 to the 4 kilograms. Our final velocity is 0 minus 0.40 meters per second. And our force is equal to 320 newtons, delta T. So we can just do our 6 times 10 to the 4th times our 0.4 So this comes out to be 24,000 on this side is equal to 320 delta t. So we divide this by 320. And so then delta t comes out to be 75 seconds. That's how long it took to stop. Then the next question is, well, how far would it move? Well, if we take a look at it, momentum and impulse, there is no d. So this comes down to not being a momentum impulse question, but a kinematics. So we know our initial velocity is equal to 0.40 seconds. Our final velocity is 0 meters per second. Our time is equal to 75 seconds. So what we can do is d is equal to our v minus v naught. No, v naught over 2 times our time. So our d, our final velocity, so this is 0, and this is 0.40 divided by 2 times our 75. 0.4 divided by 2 times 75, that's equal to, because what we have, we don't have acceleration for this, so this is our kinematic equation to use. This is our v average, which is v naught plus v divided by 2. Just a reminder of that. Yeah, you have to remember your kinematics. Kinematics shows up all the way. All right, question number 5. What average force will stop a hammer with a momentum of 48 Newton seconds in 0.03 seconds? All right, so this is, think about you have a nail, and the nail's in a piece of wood. And you have the hammer that's coming down. And the thing is that the hammer pounds the nail in, and that uses some force, and the force to pound it in. And so here we have a V naught, and we have a V final, which would be equal to 0. And through what we have is a distance, we have a change in momentum, we have a force that's acting on this. Okay? All right, so impulse is equal to our change in the momentum, and V is equal to our force times our time. So the question is, what average force? So F is what we're looking for. Make those vectors. We'll stop a hammer, so that's a V is equal to 0 meters per second, with a momentum of 48 Newton seconds. So P is equal to 48 Newton seconds in 0.03 seconds. So our time is equal to 0.030 seconds. Well, this is really our change in momentum. The momentum when it stops is 0, so our momentum is just the momentum that we had before. So, well, we could say that this is delta P, so this would be P minus our P naught, and our P is going to be equal to 0, and this minus 48 is equal to our force that we're trying to find in 0.030 seconds. And what we get is a value of negative 1600 newtons. What we get? Well, what do we mean by negative? Well, if this is the direction that's positive, that's where we have this positive momentum, then the force that's acting on this is going to be going in the opposite direction to stop it, because it has to stop it, and there's the idea of the negative sign. Now, in the book, they don't have the negative sign. Well, that's fine. But just because the negative sign is there to tell us direction. And so we could say 1600 newtons going upwards. They don't talk about direction or anything like that. They're sort of slacking on this one, I would say. But it's, how particular, how picky are you at any point? Anyways, here we go. Question number 6. A stone of mass 10 kilograms slides along the ice. All right, so this is a curling question. Like, you really have to, where else do you find stones sliding across the ice, right? So if it's a curling, I have no idea how heavy a curling, what the mass of a curling stone is, but hey, we'll say 10 kilograms. That sounds good. A stone of mass 10 kilograms slides along the ice in a straight line with a constant velocity of 8 meters per second. All right, so we have a mass is equal to 10 kilograms. We have an initial velocity that's equal to 8 meters per second. A force acts upon it for 2.5 seconds, so delta t, which is 2.5 seconds, and the velocity changes to 2 meters per second, so our final velocity is 2 meters per second. Put in our vector signs there. So question number 1, what is the momentum before, and what is the momentum afterwards? So P before equals mv, so that's equal to 10 kilograms times our 8 meters per second. So that would be equal to 80 kilograms meters per second. Afterwards, again, we'll have our mv, but now we'll have 10 times 2 meters per second. Give myself some space. That's equal to 20 kilogram meters per second. This is P after. This concept of P before and P after is, well, we've been using it in terms of impulse. As we get into the conservation of momentum, this becomes an important concept. So then B, calculate the impulse on the stone. What is the impulse? Well, impulse is equal to our change in momentum, which would be P minus our P initial. So that would be equal to our 20 minus our 80 kilogram meters per second. And 20 minus 80, well, it's equal to negative 60 kilogram meters per second. Or we could say that's equal to negative 60 Newton seconds. Both are fine units. Now the book just used this one, but this would be perfectly fine as well. Though I guess in impulse, normally we would think of impulse in terms of Newton seconds, but it can be a change in momentum. And my marking, either of these are going to be fine. You might find some people that are sticklers who say, well, we're talking impulse, it should be Newton seconds. But I don't, if things are equal, how can you take preference one over the other? And then it says, calculate the impulse acting on the stone and see what is the magnitude and direction of the force. So what is the magnitude and direction of the, I just got an email, that's why it pops up there. So our impulse is equal to our change in momentum, and that's equal to our F delta t. And going back here, what we have is the impulse is negative 60 seconds, 60 Newton seconds. And what we know is the force acts upon it. Sorry, just pulling pieces of, for 2.5 seconds, pulling pieces of information together just so I got this. So our force then is 60 divided by 2.5. And so that's equal to a negative 24 newtons. So the magnitude, the direction, the magnitude so the magnitude is 24 newtons, and the direction is backwards. Go away, go away, go away. Okay, there we go. That's it. Questions 1 to 6. Hopefully that helps. And again, if you have further questions, please talk to me. Please ask. I'm so lonely. It's okay. Anyways, there you go. Hopefully that helps you out. And as you're going through this, have a great day.